All right, welcome everybody. Hope you're having a good day. Homework 2 is available now on the Blackboard website, closed conduit flow, so you need to upload that before Wednesday. The grader has the solution to assignment 1, and I expect that probably that'll start to get scored over the weekend. And so I just want to let you know that even though I'm not the one who's doing the grading, I take responsibility for your scores on the homework assignment. And so if you think that the grader has made a mistake in scoring your work or didn't understand a certain thing that you did, just bring it to my attention and I'll have a look. I want everybody to feel like that they got the points that they're entitled to, and that's not to say that I relish the thought of like too much finagling for half a point here and half a point there. In the end, it rarely matters, but the underlying commitment that I have is I want you to get the points that you deserve. So if there's a problem, please let me know. Today we're going to begin on section 8 in the book, and continue talking from section 8 because the iterative spreadsheet design that we did on Wednesday was related to those ideas. But we're also going to continue into playing around with some of the other empirical resistance equations besides the Darcy-Weisbach equation. They're not as accurate, but they are simple to use, and so we should get some experience and practice, and you'll most likely encounter them when you take the FE exam. So it's important to know all 3 methods for calculating frictional losses. Are there any questions related to these announcements? All right. So you maybe remember the spreadsheet process that we went through last time, and just to refresh your memory, what we did in that spreadsheet was we went through a process of guessing an F value and determining the required pipe diameter based on that guess, and then we improved our guess. And the way that we improved it was by calculating what would be the flow velocity at that diameter, and what would be the relative roughness at that diameter, and getting a more accurate estimation of the F value than the initial guess we started with. And so over and over again we went through that process of re-updating the F value and getting a new D, and eventually the solution converged, meaning that the F value was no longer changing between the starting and the end of an iteration, neither was the diameter. So at the end we converged on some answer, and it gives us good accuracy, but it can be a little bit cumbersome to iterate like that. And so I wanted to draw your attention to a formula that you can find in the textbook. It's the so-called easy approach to solving for diameter, but when you look at the complexity of that formula, I don't know that it's anything but easy. The results are usually within about 5% of when you do it the full-fledged accurate way, and it has a wide range of applicability. The Reynolds number can be from 3,000 up to 3 times 10 to the 8th, and so that's the full range of applicability that would be possible for the Colebrook equation as well. So just to get an idea of what that formula looks like, I wanted to show you. Let's see, I think I have it here. The explicit approach for the previous example that we had before of where we want to put 300 liters per second through a 40-meter pipe, and the K sub S is 0.26. So this process for that same example would give us an output diameter of 1.75 meters. And so let me just show you what makes it a little bit tricky is that we've got sequential exponents. Everything has its own exponent, and sometimes it's an exponent with an exponent that is then taken to another one in the end. But as long as all the parentheses are in the right spot and you don't make a mistake along the way, you can substitute the length, flow rate, kinematic viscosity, the known head loss through the pipe, the roughness of the pipe, put all those parameters in, And the 1.75 meters compares pretty favorably to the spreadsheet method that we went through. When we went through the spreadsheet method, the end diameter that we calculated with the spreadsheet was 1.71. So that's easily within the 5% that we typically would hope to see. So this is the easy way. There's the iterative way using a spreadsheet, and then there is the explicit equation that doesn't require iteration. Okay, now we have a couple of different frictional loss methods, and when we have the computer do it, like if we're doing some automated design using water gems or other hydraulic design software, we'll just always tell it to use the Darcy-Weisbach equation because it's most accurate and it's most flexible. And by flexible, what I mean is it's applicable over a range of temperatures. The Darcy-Weisbach equation is valid for a wide range of pipe sizes. And it also works for liquids other than water. And you can't say the same thing for the other methods that we're going to take a look at today. They're not as flexible as the Darcy-Weisbach equation. But, of course, the real problem with the Darcy-Weisbach equation is the chicken and the egg situation we find ourselves in, where we don't know the F value until we know the velocity, but the velocity depends on the head loss, and you can't calculate the head loss without the F value, but you don't know the F value till you know the velocity, and so on and so forth. So the Darcy-Weisbach equation is complicated because of that. And we can estimate the F value with the Jane equation, but even when we have an explicit method for F, sometimes we still have to iterate in hydraulic design because there may be multiple pipes that the flow is going through. So it can get complicated with the Darcy-Weisbach equation. Things are simpler with the Hazen-Williams equation because this equation was calibrated over a narrow range of flow conditions rather than being broadly applicable, and the Darcy-Weisbach equation is responsive to changes in temperature or changes in viscosity or changes in diameter. It can handle anything we throw at it. The Hazen-Williams equation can't handle anything, but it's pretty good for typical conditions in a drinking water distribution network. And so the water that flows through the pipes underground to get water to your house, usually water is flowing through pipes that's within this range of diameter. Now, ordinarily, it would be uncommon for a drinking water delivery pipe to be smaller than 5 centimeters in diameter. And for that matter, it's pretty uncommon for a pipe that's carrying water to be larger in diameter than 1.85 meters. There are a handful of places, the water that flows to New York City from a reservoir upstate is much, much bigger than that, but that's a large urban area with a single water source, and so that's the exception rather than the rule. Probably in West Virginia, nearly all flow condition pipe diameters are going to be in this range. So the same thing is true with the temperature. 16 Celsius is the specific temperature that this equation is calibrated to. And you may be wondering, well, why a temperature? Temperature wasn't a factor in the Darcy-Weisbach model, and it's not directly, but of course temperature affects viscosity. And so we do need to know the viscosity of the water when we calculate the F value, because viscosity is one of the terms that goes into Reynolds number. And whether it's the Jane equation or the Colebrook equation or whether it's a Moody diagram, we have to know the kinematic viscosity in order to calculate F. So Darcy-Weisbach actually is sensitive to changes in temperature, whereas Hazen-Williams, they just calibrated it for 16 Celsius. There's no sensitivity or adjustments for temperature. And then this upper limit of 3 meters per second, that's pretty fast. Certainly there are water networks out there where the water is flowing at more than that, but they're probably not very often is the flow that high. And the reason is that if you have water flowing through a pipe that fast, then you're going to be experiencing a lot of energy loss. And so you'd be losing pressure so quickly through a pipe of that size, it wouldn't be common for it to be intentionally flowing at that speed for very long. It may be for just a brief moment when there's a peak flow, like let's say a fire in a certain area. You know, if the fire department is taking water out of a hydrant, they may be draining the pipe as quickly as water can flow through it, and maybe you will see 3 meters per second in that case. But the point is that Hazen-Williams is pretty good. It's easier to use because the F value equivalent, which is a C value in the case of the Hazen-Williams equation, it's constant. It depends on the pipe material, and it doesn't depend on the temperature, it doesn't depend on the flow velocity, it doesn't depend on the diameter of the pipe. There's just a given C value for whatever the pipe is made out of. The formulation of the Hazen-Williams equation is different if you're working in SI versus the traditional British gravitational units. And so you can see both on the screen there. And so the SI equation is different from the BG equation, but really these two formulas are the same thing. It's just we're rearranging for a different variable. And so if we know that S sub F is the slope of the energy grade line, and then recall the slope of the energy grade line is the head loss per unit length. So if we just substitute in H sub F divided by L here, then we could solve for H sub F, and this is what we end up with if we're trying to find the head loss through a pipe of known length, when the flow velocity V is known for a certain diameter, and the Hazen-Williams equation constant C is known. So the two different versions of this equation that's shown is you're solving for what will the flow velocity be if you know the pipe's hydraulic radius and slope of the energy grade line. So this first equation tells you the flow velocity through the pipe if you know a certain energy grade line slope, whereas this is if the velocity is known, how much head loss will there be. Same equation, just rearranged. Any questions so far? Okay, so let's use the Hazen-Williams equation. We have water coming from a tank where the water surface elevation is 103.5 meters. And we will assume that that tank is vented to the atmosphere, meaning that the water inside that tank at water surface elevation 103.5 has no gauge pressure, so P1 is 0. The velocity in the tank, maybe the water level is going down very slowly in the tank, but effectively the velocity is 0. We don't have any information about how quickly the velocity is going down inside that big tank, so we'll assume it's 0. And even if it wasn't, if the velocity was going down 1 centimeter per second or something like that, velocity head is usually a pretty small part of the overall energy. If you have 1 centimeter per second, so 0.01 meters per second squared divided by 2g, there's going to be essentially no energy wrapped up in the kinetic energy at location 1. All right, so we want the water flowing through a 760 meter section of cast iron pipe where we can go to a table and look up the Hazen-Williams constant for cast iron. And so what I'd like you to do is calculate the water pressure at the pipe when the flow rate is 11 liters per second. And so it's just before the water comes out of the spigot, because of course we learned from fluid mechanics last semester that when the water comes out of the spigot and it's just a jet of water, then it will have no pressure. So we're talking about just immediately before the water comes out of the spigot, then what's the pressure there if we have a flow rate of 11 liters per second. So you're going to use this formulation of the Hazen-Williams equation to calculate the head loss. You'll put the head loss equation into the energy equation, and you're going to solve for P2. Now the water is flowing through the pipe, and so Z2 is given with the elevation of 55. V2 shouldn't be canceled out. So you're going to have to calculate what's the flow velocity through the pipe and use that both in the head loss formula and also in the energy equation formula, because V2 won't be canceled out. All right, I'm going to put you into the breakout rooms. I hope you've printed out the notes by now, because I think when I put you in the breakout room, you can't see my screen anymore. If you don't have this example printed, what you could do is press the print screen button on your computer. So if you push that right now, PRTSCN, then you could paste it into Word or Paint or an image editor or something. All right, I'm going to put you in these breakout groups and ask you to collectively figure out what is the snipping tool, the pressure downstream. So let's look at the solution for this one. The water is flowing through the pipe, and we're losing pressure in the direction of flow because of head loss, but the spigot downstream is at a lower elevation, so that would promote an elevated pressure downstream. So it's kind of, we've got to see how do things cancel out here. So let me bring up the solution. All right. No, that's not the one. We're looking for pressure. That's the one. All right. So you can see that the water's flowing from the tank where the pressure is 0, the elevation is 103.5, and the velocity at 1 is 0. The water flows through the pipe, and we can calculate the flow rate with Q divided by the area. So that is, if we have the cubic meters per second and divide it by the cross-sectional area of the pipe, then that gives us 1.40 meters per second as the flow velocity. Now, substituting that into the formula for head loss, this pipe length 760 meters, the diameter for 100 millimeters is 0.1 meters down in the denominator, flow velocity and the C sub h. So we get that there's 17.54 meters of head loss, but the water was flowing downhill and the elevation decrease was more than that frictional head loss. And so the water is still going to have pressure downstream because there was a bigger delta Z to offset the head loss. So you can see rearranging the energy equation where I'm canceling out the P1 term, canceling out the V1 term. Likewise, there's no pump, there's no turbine. I didn't even bother to write the turbine term in here. You'll have pumps a lot more often than you'll have turbines. I accidentally canceled out the P2. I later amended that to say, no, we're not canceling it out, we're keeping it. Z2 and, oh, I canceled out the V2. That's embarrassing. I shouldn't have done that. I should have left the V2. So for those of you who did leave the V2, how close to this pressure of 303 kilopascals did you get? Was it similar if you'd left the velocity head in there? Let's just find out what's the magnitude of the velocity head. So if we have the velocity is 1.4, so that's 1.4 squared divided by 2g, so that's 2 times 9.81. So that should be 0.1 meters of head. So if I subtract out, so it would be Z1 minus Z2 minus HF minus V2 squared divided by 2g. So I think it reduces the available head by effectively 0.1 meters. So 30.96 minus that times 9790, 302 kilopascals instead of 303. So now I think you probably get my point about how velocity head is usually a pretty small component of how much energy is in the system. It certainly makes sense for us to cancel it out in the tank, but even when the water's moving at a pretty good speed, the velocity head is not quite negligible, but certainly the error that's built into using the Hazen-Williams equation, you know, like maybe it's accurate within 3 or 5%. So, all right, Gavin says, does Q in not equal Q out? Yeah, Q in does equal Q out, depending on like where you're drawing the control volume. So if you're drawing the control volume around the tank, then Q in is 0 and Q out is 11 liters per second. But if you draw your control volume at some section of the pipe, then yes, flow in equals flow out there. But between canceling out the velocities. In the energy equation, you can cancel out the velocity head if the velocity is 0 at location 1. Usually you cancel out the velocities if the velocity is the same. It's not a matter of flow in or flow out, it's just if the velocities are the same. So like if location 1 was in the pipe and location 2 was also a spot in the pipe, then you could cancel out the velocities. But all right, so a related problem, this next one says, let's find the flow rate in this case. It's still the same 103.5 meters of water surface elevation at the tank. And at the spigot, it's still 55 meters of elevation. And we want to find out what's the maximum free flow rate. Like if we opened up the valve all the way, and so in this, you're going to be using the other version of the formula, this time solving for V. And so now think about how we've defined in the past what is H sub F. H sub F, I'll give you a pretty direct hint of what to use for H sub F, and it's here. In this sketch, what we saw was that the head loss was simply all of the energy at location 1 compared to all of the energy at location 2, where the energy at location 2 was just the elevation of the building if the water's flowing to the top of the building and stopping. And so now in this example, the slope of the energy grade line is going to be related to the elevation difference. Well, just as an experiment, let's try the breakout rooms again. And boy, if it's going to always be half it works and half it doesn't work, then I'm not so sure that we'll continue through the semester with that. But let's give it a shot. So this time we're solving for the flow rate. And so once you get the V, the velocity, you'll have to multiply it by the cross-sectional area of the pipe. Let me put you in the breakout rooms here. Where it's certainly advantageous for us to assume that the velocity head is negligible, in particular because we're solving for V, and so V is the output of the energy loss formula. But if we didn't assume that V2 was canceled, then that would be also an unknown in the energy equation, and so V would exist in two places. And so let's just assume that V1 and V2 cancel out, and the H sub F that is going to go into the slope of the energy grade line is just the elevation difference. All right, so to find the unknown flow rate, we say that the elevation difference is H sub F. So as the water flows through the pipe, it's losing the energy that's equal to the energy, the elevation difference between the inlet and the outlet. And so then on a per unit length basis, we can find the slope of the energy grade line. The hydraulic radius of a circular pipe that's flowing full is d divided by 4. And now put all of that into the Hazen-Williams equation, and the velocity for the flow is 2.44 meters per second. And then if you multiply that by the cross-sectional area of the pipe, in this case we'll get 19.2 liters per second. And so the response of the system, if the tank is raised, so if you are doing like a design and you decided to put this water tank higher on a hill or lift it up above the ground elevation even further, then that would increase the flow rate that's going to be able to go through the pipe. Or if you made the pipe diameter larger, that likewise would increase the flow that can go through the pipe. Or if you made the pipe out of a smoother material that has a higher C value, then that would increase the velocity and accommodate more flow. Okay, so that's just an example of how to use the other version of the Hazen-Williams equation. The other approach to empirical friction loss formulas is the Manning equation. And Manning's equation is mostly used for open channel flow. We don't often utilize it in closed conduit flow. The occasional exception to that being is if it's water going through a culvert. And culverts usually only, most of the time, are going to flow partly full. But when there's a lot of rain, it's possible that a drainage network like a storm sewer or a culvert could be flowing full. And so in those cases, occasionally people might use Manning's equation for closed conduit pipes. Rather than a C value or an F value, the friction factor in Manning's equation is called N. And you'll notice that the friction factor N is in the denominator of this formula to find the flow velocity. And so that means that relatively smaller N values are for smooth pipes, and a large N value is for a rough pipe. And so that if you have a large N value down in the denominator, then that would decrease the velocity that's possible through the conduit. What we use Manning's equation for most of the time rather than closed conduit pipe would be open channel flow, like water going through a canal. This is just refreshing your memory of a trapezoidal channel geometry, or sometimes putting water through circular pipes that aren't flowing full. And the geometry for that is pretty tricky as it ends up. At the end of the semester, we'll spend just a little bit of time handling how you can find the cross-sectional area, the depth, and so on when you have water flowing through a circular pipe, but then there's air in most of the pipe and just a little bit of water. So just to be aware that Manning's equation is our other option. Now here is a C value taken from the text that has a roughness coefficient and a corrugated pipe. It depends on what the material is. Like there's a plastic corrugated pipe where the corrugations are on the outside, but it's a smooth lining on the inside. And so for that plastic corrugated pipe, it would have just a typical N value of 0.013. But for like galvanized steel culverts, the N value of 0.024 I think is pretty common. So it's kind of halfway between what you'd expect, because corrugations can be pretty large. You know, the diameter variation for a corrugated pipe may be on the order of inches. And so, you know, the effect isn't that dramatic in the N values that you'll find. There are tables that manufacturers will supply when you're doing design So you'll never be in doubt. You know, if you're in a design scenario and someone's trying to sell you a pipe for that design, they'll always be able to give you the hydraulic performance of the pipe. Okay, well, that's it for today. Just a suggestion that if you get an early start on homework 2, then that'll give you plenty of time to ask questions and iron out any uncertainties you might have. Appreciate your attention. Hope you have a great weekend, and I'll let you know in class on Monday if I hear anything from IT about these audio problems we've been having in the breakout room. So hopefully we can get that resolved. Take care, everybody.